Hi guys. It's very funny. There's a bit of a delay. But if you have questions, just type them in now. I have some questions I'd like to go through with you too. So funny. There's a bit of a delay. If nothing comes through, just send them along. Just type them in now. All right, so let me get started since I'm not getting a lot of questions yet. Let's start with gram formula math. All right, so I have a couple questions. I'll set up over here. Okay. All right, so it's backward. That's not going to help me. Let me think about that one. All right, so I can show you my screen. I'll open a PowerPoint with the questions in it. All right, screen share. Okay, so let me make sure you can see this. That's crazy. It's like a wormhole. All right. So first question I have is find gram formula mass of Al2CO3. All right. So the way you can do this, we need to find the mass of aluminum. The mass of aluminum is 27. 2 times 27 because you have 2 aluminums. You should have 3 carbons and you should have 9 oxygen molecules. All right, when you add that all up, you should get 234 grams per mole. Okay, how many moles are in a sample that's 100 grams of that, what we just found out? So that had 234 grams per mole. So you need to use the mole formula. And I'll show you the mole formula. So let me stop sharing for a second. All right, let's see. Any comments, guys? Come on. Help me out here. Any comments, guys? All right, so Al2CO3, that mass is 234 grams. Okay, so let me show that to you again. Okay, so to do this, you need to have 2 aluminum. There are 3 carbons, and there are 9 oxygen molecules. 9 times the mass of oxygen, which is 16. 3 times the mass of carbon, which is 12. And then 2 times the mass of aluminum, which is 27 grams. You add all of that together. Total is 234 grams per mole. Okay. Now, they're asking you how many moles of aluminum carbonate you have. So you have to use a mole formula. Okay, and let me bring that up for you. Right. Okay, so all of our formulas are on the last table T in our reference table. Mole calculation, number of moles is given mass over gram formula mass. All right, so 100 gram sample, they're asking you for number of moles. So number of moles is X is equal to your given mass, which is 100 grams, over your gram formula mass, which we just found up here. Okay, and that will give you the answer of 0.01 mole. All right, and if you're not getting these numbers, you need to work through your math again. Okay. All right, so let's move on to the next one. So you need to remember that the gram formula mass for aluminum carbonate is 234. So I'm just going to carry that along with me. All right, how many grams of aluminum carbonate are in a 3 mole sample? So we're going to use a mole formula again, and that's number of moles is equal to given mass over gram formula mass. They tell you that you have 3 moles, so 3 is going to be equal to given mass, and that's what you're looking for, how many grams. So given mass, I'll just make X over 234 grams per mole. So X will become, I have that here, 702 grams. Now with this one, you have to be careful because this is going to be cross multiplying. Okay, and some of you struggle with that. Okay, so just be aware of it. So X, let me underline it. Okay. Okay, so 3 is equal to X over 234. You need to put 3 over 1. And then you're going to cross multiply these two. Okay, let's see if I can make a shape. I don't want to fill it in. Okay, so you're going to cross multiply X and 1. Let's see if I can get them in there. Right, cross multiply those two, and then you're going to cross multiply 3 and 234. Okay, so 3 and 234, and that will give you 702 grams. Okay, so let me check out how you guys are doing. Not getting any comments, which, you know, is a little rough. Thanks. So let's see how that's going. Okay, let's see. Let's do the next one. The next one is going to be dealing with the same stuff. So let me bring this along with me. So this is gram formula mass of aluminum carbonate. All of these questions have aluminum carbonate in it, so that's why I'm carrying these along with me. All right, so gram formula mass of aluminum carbonate is 234. We know that. Let's just hold on to it. All right, what is the percent composition of aluminum in aluminum to carbonate? All right, so gram formula mass is 234, but it's asking for percent composition. So percent composition is part over whole times 100. Okay, so let me format that again for you. Okay, all right, so to set this up, it would be part, which is aluminum. So what does aluminum weigh? So aluminum weighs 27 grams, and you have 2 of them. So 27 times 27 is 54, so it'll be 54. And we're going to multiply everything by 100 at the end. So let me get that in there. So 54, that's funny, it did the calculation. All right, so 54 over the whole, and the whole is gram formula mass. It's what everything weighs, 234. All right, 54 over 234 times 100 is going to equal 23%. Okay, and that's percent composition of aluminum. So 23% of aluminum carbonate is aluminum. Okay. All right, what if aluminum carbonate was a hydrate? Okay, so if it's a hydrate, you have water added to your salt already. I don't even know if this one exists. It doesn't matter. All right, so I need a text box. Okay, I'm going to hold on to this mass again. All right, so the mass of aluminum carbonate we know to be 234. Now we have the addition of water. So total mass of salt. Okay, now the hydrate part. Water equals 7 water molecules. How many hydrogens? We have 14 hydrogens plus how many oxygens? 7. Be careful with the coefficient. 7 oxygens. Okay, and this whole thing is going to equal, I'll just give you the number here, 126 grams. So that's the water. That is not the whole. That is the part. All right, so percent composition is part over whole times 100. Let me grab that over here. Grab all of it. Okay. Oops. All right, so part over whole times 100. The part is the water, 126 grams. And the whole is the salt, so aluminum carbonate, plus the water. So we need to do 234 plus 126. And we're going to multiply all that by 100, and that will give you your answer. Okay, so that answer is 35%. So 35% of this is water now in the hydrate. So if I were to do that experiment that we did in class, a hydrate lab, and I heated this sample up, I would evaporate all the water off. So what I would hope for if I had 1 mole sample would be a mass of this 234 plus 126 in the beginning. And then if I heat it up, I should lose the 126 grams if I have a mole sample, which is a lot. All right. So if I do that, then I'll have, 100% yield. I'll be yielding exactly what I've made. Okay. All right. So let me check out how you guys are doing. Okay. No comments. I think we're doing good. I hope so. I mean, comments if you guys don't understand something that I'm doing. That'd be really helpful. All right. Let's continue. I think I have one more on my slides that I could do with you. All right, so balancing seemed to be something somewhat of a trouble in class. It always is, no matter who you are. The honors class struggles with it. AP, Chem will struggle with it. It's just guess and check, so it never feels right. But you have to keep working through it. So like I said in class, you got to set up a T-chart, you write all the atoms down, and you balance, and you keep changing coefficients. You never change subscripts, right? Because H2O is not the same as H2O2. All right. Here is a multiple choice type question that they can ask with balancing. Which equation shows a conservation of mass? And we talked about conservation of mass. That means whatever you put in, you're going to account for coming out on the other side of the arrow. All right, so these are reactions occurring. So the conservation of mass would be a balanced equation. So which one's balanced? Okay, can you guys figure that out? It's one of these answers. I like singing. All right, so let me balance it out. All right, let's try the first one. We have 1 Na on the left, 1 Na on the right. We have 2 Cl's on the left and 1 Cl on the right. So it's not A, it's not balanced. All right, B, we have 1 aluminum, good. 2 Brs, 3 Brs, not balanced. All right, C, 2 hydrogens, on the left, 2 hydrogens on the right, 1 oxygen, 2 oxygens, not balanced. All right, so is it looking good for D? Let's just double check it. So 1P, 1P, 5 Cls, 3 Cls, and 2 Cls. Now we have 5 Cls. All right, do you see that it's balanced? All right, so those are balancing type questions. Let's see, are there any other questions I can give to you? Okay, I'm going to. Okay, so I'm here. All right, any questions, guys? Or are we good? All right, I'll share this PowerPoint with you on, let's see. So I'll share this PowerPoint with you on our Google Classroom site, so you have access to it and everyone will have access to it. Okay. All right, other questions that we may go over here. Oh, empirical and molecular, I didn't do one of those. All right, so let's see if I can grab a question for you. Okay, let's see, empirical, molecular. I hope that screen shared with you. I don't know if it did. So I may just seem like a crazy person talking about nothing that you can see. All right. Screen share this one. Share. Okay, back to my PowerPoint here. All right, which pair consists of molecular formula and its corresponding empirical formula? All right, so you need to break them down to figure out which one is right. All right, so right off the bat, the first one, it's CH3CH3. That is totally different than CH. So that one's a totally different formula, okay? It's a structural formula, is different. B, C6H6 and C2H2. Can they both be reduced to something that's the same? So I can reduce C6H6 to CH by dividing by 6 all of the subscripts. So that becomes CH, empirical formula. C2H2, I can divide by 2 the subscripts, and that becomes CH, which is the same empirical formula as the first one. So I think the answer choice is B. Now, I don't think it's going to be correct because it says it's a molecular formula and its corresponding empirical formula. Both of those can be reduced, so both of them are not empirical formulas. So it's not going to be answer choice B, even though it looks correct, okay? So that's a distractor. C, P4O10 and P2O5. So P4O10 can be broken, you can divide by 2 for each of these and they become P2O5. P2O5 is an empirical formula, so C is the correct answer. Okay, and I hope you can see that. So empirical means lowest terms. You cannot make the subscripts and the ratio any smaller. So P, for every 2 P's, there are 5 oxygens, and I can't go any lower on my list here. Okay, let's see if there's another question that we'd like to do. All right, so this is a structural formula. We didn't talk about this much in class, but I did in the video. Oops. All right, so a structural formula shows you how the atoms are together, or how they're oriented in a compound. So to find an empirical formula from here, you would have to count up everything. So there are 4 carbons. There are 10 hydrogens, so 4 carbons, C4, H10, O2. Now that's a molecular formula, and I know it's a molecular formula because I can divide the subscripts by a greatest common factor. So again, the molecular formula for this would be C4H10O2, divide by 2, everything. So it becomes C2H5O. And that is answer choice B. Okay, any other ones that we can do together? Okay, molecular formula of glucose is the following: C6H12O6. C6H12O6. Now, to find the empirical formula, we need to divide by the greatest common factor, which happens to be 6. So it becomes CH6O. Oh, no, I did that wrong. So it'd be C6H12O6 if you divide all by 6. Now, this, I made a mistake that everyone always does. All right, divide everything by 6. 6 divided by 6 is 1, so it's C. H12 divided by 6 is 2. And oxygen 6 divided by 6 is O. So it's CH2O, which is an empirical formula of glucose. Okay. All right, so what else do you need me to do? That's what I want to figure out now with you guys. All right, I will find something for us to do. All right, so which pair of compounds is the same empirical formula? That's a similar question to the other one. Let's find another one. All right, so a compound whose empirical formula is NO2 could have a molecular mass of blank. All right, so let's do that one. Okay, so a compound whose empirical formula is NO2. So the first thing to do is find out what NO2 weighs. And a molecular formula could be that weight, or it could be a multiple of that weight. So N weighs 14. Oxygen weighs 16, but I have 2 of them. 32 plus 14 gives me 46 grams per mole. All right, so 46 could be an answer. You can't go lower than 46 because that's the empirical formula. That's what it weighs. It cannot get lower. That's what empirical means. It can be a multiple of this, though. So 46 times 2, where everything is multiplied by 2. That molecular formula would be N2O4. Okay, if you need to understand what I'm doing. So that weighs 46 times 2 weighs 92, which is answer choice C. And that would be correct. All right, any other ones? All right, let's do 35 here. Okay, the empirical formula of a compound is CH2. The molecular formula of this compound could be what? So it has to be a multiple. So for every 1 carbon, there are 2 hydrogens. So you have to compare them. It cannot be A, because for 1 carbon, there's 4 hydrogens. B, C2H2, that empirical formula would be CH, because you divide both subscripts by 2, and that's not the answer. C2H4, I can divide both of those by 2. It becomes CH2, which is the answer to this question. C3H3, if I divide by 3, becomes CH, which is not the same as CH2. Okay. All right, let's see how we're doing. Oh, how do you find a molecular formula from an empirical formula? Excellent question. I think I got that in the last one. But let's try another one. So if I give you empirical formula, let's see, empirical formula Let's do CH2O like I showed you before. I see H2O. Okay, that would be an empirical formula. And that would weigh a certain amount, and we could figure that out. So carbon weighs 12, hydrogen weighs 1, and oxygen weighs 16. So if we add those up, 12 plus 2, 14, 16, 30. 30 grams per mole is my empirical formula. Now, if I tell you I have another compound, and it's a molecular formula, what is it? Molecular compound that has an empirical formula of CH2O. Oops. And it weighs 90 grams per mole. That means my ratio has increased by a certain amount. All right, so 90 grams per mole is what this one weighs. It's not 30. If it was 30 grams per mole, it would be CH2O. It's 90. So 90 grams per mole divided by what the empirical weighs. Oh, you silly underline. The empirical weighs 30 grams per mole. So if you do 90 divided by 30, you will get 3. And that tells you all your subscripts are going to increase by a factor of 3. So it becomes C3H6O3 because everything's multiplied by 3. And let me make those subscripts there. I hope that answers your question. Do you need me to do another one? Okay, so let's do gram formula mass again and percent comp. I think that'll help us too. Let me make sure you're all good. Oh, balancing problems, I can do those too. All right, so let me do gram formula mass quick. All right, so gram formula mass is just what a mole weighs. So you add everything together. So let me do an easy one. Let's do H2O. What does H2O weigh? What's the gram formula mass of H2O? Subscript here. Okay, so you have to account for every atom. There are 2 hydrogens, and there is 1 oxygen. Okay, hydrogen weighs 1, and oxygen weighs 16. Okay, now I need to add it together, and that will be my gram formula mass. So it's 18 grams per mole of H2O. Okay, now if I want to do percent composition of hydrogen in water, so in H2O, it'd be part over whole times 100. So the part would be hydrogen, and you have to count all of them. So you have 2 hydrogens in this water molecule, so it would be 2 divided by the whole, which would be 18. Oh, struggle. 18, and everything needs to be multiplied by 100 because it's a percent. Okay, so 2 divided by 18, what is that? That's 9 times 100 gives you 9. No, that's not right. 2 divided by 18, not 18 divided by 2. So 2 divided by 18, let me get my trusty calculator, is 0.11 times 100 gives you 11%. So 11% of this water molecule is hydrogen. Okay, which means that the other percentage is whatever is in the compound left, and that's oxygen. So oxygen makes up the whole rest of that percentage. Okay, let's balance because we want to balance, right? Right, balancing. Let me go find a balance question. Balancing is so much fun, guys. I don't know why you hate it so much. No, I do, because I used to hate it. Because it's never fun. All right, some of them can be really hard, and unfortunately, this is the way it is. Oh, we have to do mole ratio questions too, if you guys need that. let's do this one, Al 2O3. Let me paste that one up here. All right, we need to balance it. The way you do it on the left and the right, you're going to have to count up the atoms. Let me get this. Oh, you silly PowerPoint. All right, text box there. All right, so that didn't work. All right, on the left, we have aluminum, and you have one of them. On the left, we have oxygen, and you have two of them. Okay, let's see if I can copy this now. Ta-da, I can. All right, except now it's over there. All right, now on the right, we have 2 aluminums and 3 oxygens. Now we have to make these equal. So I like to always balance oxygens first. I always do hydrogen last because hydrogen, they're just everywhere. So they're hard to account for. All right, so let's balance oxygen here. All right, and then I'll go back to that other question. All right, so I want to balance this with the other one. The way I can do that is, let me see if I can strike through this. Good, so I'm going to change this to something. I'd like to change this one to 6, and to do that, I don't want to strike. Silly strike. Okay, I want to change this to 6. To do that, I need to add a coefficient in the front, and that coefficient is going to be 2, because 2 times 3 makes 6. Okay, to make 6 over here, let me strike through this one again. Oh, okay, to make 6 over here, I need to add 3 to the front of this. Okay, do you see that? All right, so 3 times 2 is 6. So that's balanced, but I have the problem with the other one, aluminum. But I did put a 2 here, so I need to make sure my aluminums are reflecting what's in the actual formula now. So 2 times 2 is 4. Can I make 4 over here? Ooh, it's easy. Just put a 4 here. And now you have 4 aluminums. Balanced. Hooray. All right, and that's it. You see how annoying it can be? So if I didn't choose to make the oxygen add up to 6, I would have been wrong, right? I could have jumped to 9 and then put a 3 in the front, and that just wouldn't work. So you try the lowest first, and then sometimes you just need to up your game and just keep multiplying and throwing the numbers in there. But you always need to make sure they reflect. So when I put a 2 here and made this 6 oxygens, I also changed the aluminum. So you need to make sure that you're doing basic accounting. You don't want to lose any aluminums in the process. Okay. All right. Let me look quick. If we go back to this question. All right. So if I ask you for a percent composition of hydrogen and water, you know that the part is hydrogen because it says it in the question. All right. So I could have easily said percent composition of oxygen in water, and then the part would change. The whole always stays the same. That's gram formula mass. So the part, if I ask for water, would be 16. I mean, sorry, the part would be oxygen, 16. That's what it weighs up here, because that's what's in the question. All right, so part over whole times 100. That changes the whole answer. Okay, so I'm just going to keep this same for when I upload later. Any other questions? I will do anything that you need me to do. Okay, do you want to see more balancing? I don't know if you need to. The balancing we do isn't too difficult. It can get really intense and really really rough. But I try not to, and the Regents doesn't kill you too much with that. All right, so let's try another balance. Let's try KClO3 becomes potassium chloride and oxygen gas. All right, here it is. So let me do this again. Go away. All right, here we go. All right, so these are all going to change. All right, so on the left, I have a potassium. It's K. I have one of them. Chlorine, I have 1. And oxygen, I have 3. On the right, I have 1 K. Sorry. K equals 1. Cl equals 1. And oxygen equals 2. Do you see that oxygen is always the problem? Always. So we need to, make sure that's right. And the reason it is a problem is because it's diatomic, right? It doesn't exist as oxygen by itself. That's monatomic, remember? So O2 is always going to be like that. Same thing with chlorine and so on. But chlorine gas isn't just hanging out all the time. Nitrogen gas and oxygen gas and hydrogen gas are, but chlorine gas, we try not to have that hanging around because it can kill you. All right, so let's balance. Let's put a 3 in the front like we did before, and that becomes 6. Okay, 1, 1, 6. Over here, I can change this to 6 too, but I can by putting a 2 here, but now I need to make fancy math work. So K becomes 2 and Cl becomes 2. And then I can change these by adding a 2 in the front. K becomes 2. Cl becomes 2. Now check if you're balanced. 2 Ks, 2 Cls, 6 oxygens. And then on the right, we have 2 Ks, 2 Cls, and 6 oxygens again. All right, let's do another mole problem, and then I'll do mole ratio with you. All right, so let's do a mole problem. All right, so 2 moles of, let's do a really easy one that we can add up quick. All right. All right, so if you're given 0.25 moles of CH4, how many grams is that? Okay, so 1 mole weighs X grams, and now you got to figure out how much a quarter moles weighs. All right, so CH4, carbon weighs 12 plus 4 oxygens. It gives you 16 grams per mole. Okay, you're using the mole formula, so it's number of moles is equal to given mass over, sorry, my brain's in a frog right now. All right, given mass over gram formula mass, and that's what you calculated before. Okay, so number of moles is what they gave you. They gave you 0.25 is equal to given mass. That is what you're trying to find out. They didn't give you mass. They said how many grams or how much mass does it have. So that's X. And that's going to be over gram formula mass, which we just found out up top is 16 grams per mole. So you need to cross multiply. Okay, and I put that over 1 because it's a whole number and I can do that. Okay, and you can do that in math. So you cross multiply these. It's 1 times X is equal to 0.25 times 16. Okay, so X is equal to 0.25 times 16. Let's see if we can get that. 0.25 times 16 equals 4 grams. So you have 4 grams of CH4 in 0.25 moles. That's how you figure it out. All right. Can we go backwards? Grams to moles? All right, so I'll take the same question. How many moles of CH4 are in a sample that is 32 grams? Okay, First things first, write down the mole equation. And I'm just going to steal it from over here. The mole equation's on table T. Okay, number of moles equals given mass over GFM, gram formula mass. We also calculated gram formula mass. That's where you add them all up. Okay, so that equals GFM. Right, number of moles, that's X, is equal to, given mass, they gave you 32 grams. You're going to put that over gram formula mass, which is 16 grams per mole. That equals 32 divided by 16 is 2. So there's 2 moles in 32 gram sample of CH4. Okay, anyone else stumped? Do we need something else to do? Okay, moles, grams. All right. Let's see. Good. We're good with that. Anything else that you guys need me to do? Anything at all? All right. Let me run through my list. Here, screen share. All right. So I'm going to stop sharing that for a second. Hi. All right. So what I want to do is go through what's going to be on the test. So we have empirical, molecular, and structural formulas. You need to be able to tell the difference. Conservation of mass, which is balancing equations. Gram formula mass, which is molar mass, so calculating gram formula mass. Percent composition, which is part over whole times 100. And you need to be able to do that for hydrates as well. And remember, when it's a percent composition of water, water's the part. Okay, and the whole hydrate, the salt plus the hydrate, the water part, is going to be the whole. Mole ratios, I need to do mole ratios. And then we did gram formula mass and mass to, moles to grams and grams to moles. All right, so mole ratio, let me do that quick and then we'll be done. Okay, all right, mole ratio, let's go find a good question. Oh, I had one before. Man, there's so many here. All right. Oops. I lost the question. All right, so we're given a balanced equation. How do I know it's balanced? Because I'm assuming it's balanced, but we could do a quick math here. There's 8 nitrogens, 2 nitrogens here. Oh, no, sorry. Ooh, tricky. There are 2 nitrogens, but there's 3 total. So 3 times 2 is 6, plus 2 is 8 nitrogens. All right, so usually nitrogen being balanced here is balanced. All right, so let's go and try first one. If 1 mole of water is produced, how many moles of HNO3 are used? All right, so remember, you need to just underline what they're asking you for. So they want to know about water. So here's water. I'm going to underline it. And they also want to know about HNO3 over here. If they tell you that you have 1 mole of water, so you put the 1 mole under the water. They want to know how many moles of HNO3 are produced. That's X. So if we drag this stuff down here, it's 8. Let's get this to look pretty. And 4. I want to underline all this. Underline. 8 over X. It's equal to 4 over 1. Okay, cross multiply. 8 times 1 is 8. 4 times x is 4x. So 4x is equal to 8. X equals 2. All right, so that's the number of moles of HNO3. Good. All right. I hope that mole ratio helps you out a bunch. Okay. And that's pretty much it for your exam. I know that took me 45 minutes. Sorry for the technical situation. Okay. All right. I have a request for percent composition of water real quick. If you want to leave, you can. Thanks for hanging in there with me. All right. So let's do hydrates. I don't think I have a good one on here. So let me make one. Yeah, no, I don't have a good one. Okay, so let's do that. Let me grab that other one that I did before, and then I'll just change the hydrates. Okay, what is the percent composition of water in Al2CO33 and 7 water molecules? Let's do 2 water molecules. All right. So percent composition is always part over whole times 100. All right, so part is water. How do I know it's water? Because it says percent composition of water. So how much of this entire hydrate is water? That's what they're asking you, percentage-wise. So 100% will be the whole. So that's everything. So you add them all together. So you do gram formula mass of Al2CO33 and 2 water molecules. So Al2, you have 2 ALs. Let me put this here. 2 AL. How many carbons do we have? We have 3 carbons, and we have 9 oxygen molecules. Aluminum weighs 27. Carbon weighs 12. And oxygen weighs 16, and you have 9 of them. Okay, total is, I have that here somewhere. Total is 234 grams per mole. And that's just the salt. That is just aluminum carbonate. But we need to add the water too. So water, we have 4 hydrogens, and you have 2 oxygens. 4 times 1 equals 4. 2 times 16 equals 32. So that's 36. Okay. So let me just write out what this is. Al2CO3. Okay. So that tells you a bunch of information. Okay, when you do this. This is going to help you do the entire question. So you want to do part over whole times 100. So the part is going to be water, like I said before. So water weighs 36 grams per mole. You just found that one out. So 36 is the part. And that's going to be over the whole. So the whole is actually the salt, 234, plus the water. And all of that is multiplied by 100. And that equals a number. All right, so let me look that up. So 234 plus 36 is 270. That's the bottom. So 36 divided by 270 equals 0.133 times 100, 13%. 13% H2O in this salt, this hydrate. Okay, I hope that helps. And I think I'm going to call it quits because I'm going to put the kiddies to bed. All right, guys. Thanks for hanging in there with me. Thanks for asking questions. I hope this cleared a whole bunch of stuff up for you. All right, remember, tomorrow is just part 2. We'll do multiple choice on Tuesday. All right, thanks. Bye.